there's a need for an adaptive control. And the applications that we can mention here is aerospace, robotics, and automotive applications. That we are dealing with time-varying systems, and there are uncertainty, and using model-based controllers may be impractical. There is a limitation in existing adaptive methods. For example, if we mention some well-established methods like L1 adaptive control or MRAC, they require full state feedback measurements. On the other hand, some machine learning methods like RL-based, they heavily depend on simulations, and they require high computational demand. And for example, they need to go through many iterations, and learning a policy for stabilization and tracking may take a couple of hours. Initial formalization for RCC, retrospective, which stands for retrospective cost adaptive control, is in discrete time, and there is a need for getting the continuous time formulation, because when we implement a discrete time controller, the discrepancy that arises in between the discrete and the continuous time systems may bring some problems. So there is an opportunity for getting the continuous time formalization for retrospective cost adaptive control, and it enables us to better integrate them with physical systems and eliminating the problem that arises in discretization and sensitivity to sampling time. So we are dealing with uncertain systems. The discrete time controllers, they are sensitive to sampling time, and when the problem that we have with full state feedback controllers is that we need to have full measurement of the state, while on the other hand, output feedback controllers, they only require measurements of output. Having a continuous time formalization, it eases the analysis when we have a continuous time model and we want to implement a continuous time controller. And we can also eliminate the problem that arises in simulation sim to real gap. So consider a basic control servo loop that we have a plant. The plant is unknown. We don't know the dynamics or parameters of the model, and we want to drive the output of the model to a reference. So here we are defining the reference signal with R of t, and the objective is to bring the error between output and reference to 0. And we want to use a linear controller, and any linearly parameterized controller can be written as U of t equals phi of t times theta of t, phi of t, which is the regressor matrix, and theta of t is the vector of gains. So the regressor, it depends on the controller that we are using, and it can include integrals of output, integrals of control signal. It depends on what controller that we're using, and this method is applicable to linear controllers, so we can mention PID controllers, full state feedback controllers, and cascade TPI controllers. So the objective is to develop a continuous time adaptive method that can adapt the vector of gains, theta of t, and the objective is to achieve stabilization and tracking performance. Next, we define the retrospective performance variable, which includes the output error and filtered regressor data and filtered control signal. And for filtering these signals, we use dynamic filters like a first order low pass filter or a second order low pass filter, depending on the design specifications that we need. So we define the dynamic filter as g of f of s, and we can easily get the state space realization of this dynamic filter. And as shown in these equations, we can easily get the filtered regressor data and the filtered control signal. Finally, we define the retrospective cost, which is an integral over the output error and control signal and the gain vector. Here we have positive definite weighting matrices, R of Z, R of W, and R of theta, which are some weighting matrices of appropriate dimension. So this method is easily applicable to MIMO systems as well. We just need to get the appropriate dimensions for these matrices and the regressor data. So we define, the objective is to minimize this cost function with respect to theta of t, and because we are dealing with the quadratic cost function, we can get the closed form solution for the minimizer, and the equations for minimizer is given here, and it is all in continuous time, so we can have an adaptive control method in continuous time. As we mentioned, this method is applicable to linear controllers, and any linearly parameterized controller can be written as phi of t times theta of t. In this work, we considered nth order transfer function. We considered PID and PPI controller, and also FSFI. So in the case of nth order transfer function, the regressor matrix simply becomes integrals of control signal and integrals of the output error. Here also we are showing the structure for PPI controller and FSFI controller, and in each case the regressor can be easily computed. So for validating this method, we first started to implementing it on a double integrator. This system is quite simple yet fundamental in controls, because most of the robotic applications with some assumptions can be simplified to just a double integrator. For example, the quadrator, if you assume that the rotational dynamics are much faster, we can assume the translational dynamics to be just a double integrator. So the objective here is to bring the output of the system, which is position, to a reference signal. So we just want to follow a unit step command. And we considered second order full state feedback with integral action and PID control laws, that each of them can be written as shown here. And so the gain vector is needed to be learned with the algorithm called continuous time retrospective cost adaptive control, or abbreviated for CTR6. Here we're showing the simulation results. As you can see, the figure on the left shows the results for a second order controller. As you can see in figure D, all of the gains are initialized at 0, and we don't have any knowledge of the model parameters. And the objective is to bring the output to unit steps. So figure C is showing the output, figure A is showing the output error in logarithmic scale, and figure B is showing the control signal. In the middle, we have the results for PID controller. Again, the same scenario. All gains are initialized at 0, and the objective is to bring the output to unit step. And we are showing the control signal and also output error. And the figure on the right is showing the results for FSFI. So as you can see, that there are some controllers may yield better performance. Some of them may get destabilization in less time, and in some cases they require much time. Then we move to bicopter control problem. By bicopter in this work we mean a simplified quadrotor. So if we assume a quadcopter that only is confined to a 2D plane, we can simplify the system to a bicopter, and the equations of motion is given here. And for the flight controller, here we are considering conventional cascaded architecture, that we have an inner loop and an outer loop. And if we assume that the inner loop, which needs to deal with the rotational dynamics, is much faster, we can simplify the translational dynamics to just the double integrators. So the simulation results, we want our bicopter to follow harmonic commands. As you can see on the figure on the left is showing results for a PID controller, The objective is the position of bicopter to follow a harmonic command. And in total, we have 9 gains that need to be learned. We have 2 controllers for the position and 1 controller for the inner loop. Each controller is a PID controller, so in total we need to learn 9 gains. As you can see, all of the gains are initialized at 0. We don't have any knowledge of the parameters of the bicopter, which are its mass and moment of inertia. And the gains are getting updated in continuous time, and the position is following a harmonic command. The figure on the right is showing the results for a cascaded PPI controller, which is widely used in quadrotor applications and other aerial vehicles. In this case, the same scenario, we want to follow a harmonic command for the position of the bicopter, and the gains are all initialized at 0. Here again, we have 9 gains, and we have 3 PPI controllers, 2 PPI controller for the position of the bicopter, and 1 PPI controller for the inner loop, which needs to regulate the angle of the bicopter. Then we moved to the 3-dimensional attitude control problem. Just consider a 3-dimensional attitude control problem, and for a rigid body, and the dynamics is given as shown here. So the objective is to design a model-free attitude controller, and we don't know the moments of inertia, and we want to design a linear controller for attitude stabilization. In this case, we consider the FSFI and cascaded PPI controller architecture to stabilize each of the Euler angles. In this case, because we wanted to also validate the method experimentally, we considered an experimental setup, an airframe mounted on a 3-2-1 gimbal platform, and with also some unknown weights added to act as disturbance and adding some uncertainty to the system. And the objective is to regulate the Euler angles. So as you can see, the experimental setup here is a 3DOF, 3 degree of freedom gimbal platform. So we have a quad rotor mounted on this system, and it can freely move it has 3 degrees of freedom: roll angle, pitch angle, and yaw angle. There are also some weights added to each of the axes, so they can act as unknown weights. The moment of inertia is unknown, and we want to use the adaptive control method developed in this work on this system. For measurements for the attitude of the quadrotor, an IMU is being used. We are using a PixHawk flight controller that provides us with the measurements for the attitude for the quadcopter, and it is the continuous time adaptive method is implemented on the PixHawk flight controller. We have results, experimental results here. The column on the left is showing the results for FSFI controller. The first figure is showing error in Euler angles on a logarithmic scale for 3 axes, roll axis, pitch axis, and yaw axis. Figure C is showing the control inputs. So we have 3 moments applied to the quadrotor in each axis, and controller and the figure E is showing the gains that are being updated in continuous time. So all gains are initialized at 0. We have 3 controllers, 3 single input, single output controllers, and each of them has 3 gains that need to be learned. The figure on the right is showing results for a PPI controller. PPI controller in general for aerial vehicles yield us a better performance because we have measurement of both position and velocity, so we can have a cascaded PPI controller, and it gives us a better performance. Figure B is showing output error on a logarithmic scale. Figure D, again, the control signals. We have 3 moments that need to be applied to the quadrotor. And figure F is showing that how the gains are getting updated and learned, and all gains are initialized at 0. Here I have some videos of the experimental problem. So the quadrotor is initialized with some initial error on the Euler angles, and some unknown weights are also added, and the controller needs to learn to stabilize the attitude of the quadrotor. So as you can see, after some time, the gains are learned, and the controller was able to stabilize all 3 Euler angles. We also have the PPI controller results. Again, the same scenario. We have some initial error on the Euler angles, and the CTRCAC tries to learn the controller gains for a stabilization of the quadrotor. PPI controller seems to yield